Okay, I guess we can get started. So, hello everyone. My name is Howie, and this presentation is about Java build tooling. So the motivation for this talk is that although Java is known to be a language that is very easy to learn, have great IDE support, and be extremely performant when used in production, Java build tools like Maven or Gradle don't always have this kind of properties. So build tools often tend to be slow, they tend to be hard to learn or hard to use, hard to customize. And the IDE support for build tools, although it's there, is often not as good as you'd hope for. So for this talk, we have four sections. First, we'll talk about why are build tools hard from a user perspective, and I'll do a deep dive into some of these facets of what makes a Java build tool difficult compared to what you might expect. We'll talk about why build tools are hard for implementers, why people just haven't gone and made a better Java build tool that fixes all these problems. We'll talk about Mill, which is one of my open source projects that tries to make progress in these areas, which tries to take steps forward in improving a Java build tool experience. And we'll talk about the idea of object-oriented builds, which is one of the key ideas that lets Mill make progress improving the Java build tool like design, where other build tools have struggled with in the past. So about myself, I learned Java 20 years ago as my first programming language. I've been doing open source work since 2012. The build tool we'll talk about later, Mill, is one of my open source projects. My last job was at Databricks, which is a Scala on a JVM shop. So a lot of my projects are Scala on the JVM, but also a lot of Java and other JVM-related technologies. My professional specialty is in developer tools, so everything that happens before your code goes to production. Setting up your dev environment, locally or remote in the cloud, CI system design, testing system ID integrations, and lastly, build systems, which is the topic of the talk today. So first, let's talk about why build systems are hard for users from a Java developer perspective. To me, the problems in the build systems largely come down to the three things I mentioned earlier: the performance, ID support, and programmability. All things that Java is known to be very, very good at, but Java build tools are not. So in terms of performance, everyone says that the Go language compiles very quickly, and you press compile, go build, everything's done already. You can immediately start using your program. No one says that Java compiles quickly, typically, but when you dig into it, it's actually not so obvious. So, for example, if we take the Netty code base, who here knows what Netty is? It's an open source networking framework, clients and servers, that kind of thing. It's about 500,000 lines of code, and it takes about 50 seconds to clean compile on my 10-core MacBook using 10 cores, using Maven W. So I'm going to kick this off now in the background. Here's Netty in my terminal. We're not going to wait for it. We'll come back later in 50 seconds. And is this fast or not? Well, it's a big project. 50 seconds is kind of slow. It's hard to make a judgment. And if I try compiling a single module, you see it compiles at quite a similar rate, a few thousand lines a second. So whether you're using clean install, whether you're using clean compile, whether you're compiling everything in 10 cores, compiling one module, in this case Netty common on one core, it doesn't feel very fast. You press compile, you wait 4 seconds, and then it's ready for you to use. What people don't realize is that if you take the Java C command that Maven prints out to the terminal when you run Maven compile, it actually compiles 3 times quicker. So this is literally what Maven prints out. Like Maven runs this internally to do the actual compilation. And this, with all the dependencies already downloaded, everything ready, it just needs to compile the code. But copying the command out, running it separately, is 3 times faster than using Maven to do the same compilation. And any of you who have deployed Java in production know that running Java C or any Java application cold from the command line like this is the worst possible performance you get out of a Java program. So Java C is a Java program and runs on a JVM. And the JVM is known to have cold starts and gets good hot performance later. And by running Java C from command line, you never get the later, you just get the cold start, which is the worst possible performance you get of any Java program. And it's already 3 times faster than Maven. So if you look at how fast it could be if you run Java C hot, I have a small bench.java file I'll show you later that just does the same thing but keeps the JVM warm. It has another 5 times speed up, which is kind of what you'd expect, right? Running Java cold is really bad, but running Java hot is maybe 5 times as fast. So now we're at a 15 times speed up versus Maven, And we are using the same Java compiler, compiling the same Java code, the same dependencies. I didn't rewrite it in Rust or anything. It's the same Java C. It's just I'm using it properly rather than wrapped in this huge amount of cold JVM boilerplate. So earlier we kicked off the clean compile of the whole netty code base. You can see it took about 50 seconds here. Can you guys at the back see? Yes? So I'll make it bigger. So took about 50 seconds for the clean compile of the whole netty code base. I'm going to, if I show you the clean compile of the single module netty common, you'll see it takes about, well, this is a clean, I'm ignoring that time, but the compile will take about 4 to 5 seconds. Now it took about 4.7 with some variation. If I run Java C directly, so you're not going to type this up from the command line, the class path is very long, but let's say you just run it directly without the whole Maven boilerplate. Takes about 1.5 seconds, 1.4 in this case, 1.3 something. And if I run Java C hot, like without paying the cold JVM startup time, so I have this bench.java file here that does this. All it is a main method with a while loop, and in the while loop, it just runs Java compiler over and over. So it's clean compiling, but it's keeping a JVM warm so compiler doesn't get thrown away. You see, it started off a bit slow, but as it runs, the JVM warms up, as you know JVMs tend to do. And after a while, we're taking about 300 milliseconds to compile the same 29,000 lines of code that previously we were compiling in 4.5 seconds using the Maven build tool. So compiling a code isn't the only thing you do day to day, so there's not a total representation of a developer workflow, but it just shows how much overhead the build tool can add over what's actually a very fast and performant underlying JVM Java toolchain. Like Java C is bloody fast. It compiles at 100,000 lines a second, a million line code base to compile in 5 seconds or 10 seconds. But because it's wrapped in Maven, in Gradle, and other tools, it kind of feels a bit slow and clunky, despite Java itself not being slow and clunky. Next thing I'm going to talk about is IDE support. So all your build tools have IDE support, whether Maven, Gradle, Bazel, others, Pants too, but it often isn't quite as good as you'd hope for. So if I pull up an example, so here is the Mockito code base. Who here knows Mockito? Mockito is built using Gradle. It's an open source unit test helper library. You can see there is IDE support for Gradle. We have the nice elephant icon up here. We have some syntax highlighting in the editor. You can ask for the type signature of things. I can see it get JVM args as a list, for example. That's useful. But when you actually try to do things, let's say I try to jump to test implementation, I get this dependency handler, provider, add, create stub. So it doesn't actually tell me anything about what test implementation is. Similarly, if I jump to JVM args, I get a getter, I get a setter, or a few setters, I get a getter, and I get nothing else. So this isn't very helpful. I can't see what JVM args was before I modified the value. I can't see where JVM args is used after I modify the value. If I haven't already memorized what JVM args does, or have ChatGPT memorize for me, there'll be no way for me to use my IDE to figure out what JVM args is doing. So this is not good. And it's not just JVM args, like compiler args is the same. And earlier we saw how test implementation, compiler only, all of these drop you into these stubs that don't tell you anything. And this is in big contrast to how application Java code typically works. So I look at any random Java file in here. I expect to be able to look at anything in this file and jump to its definition, see where it's used within the program, and kind of recursively navigate. Recursively navigate around, navigate into different parts of my program, and get useful things. So I don't get stuck just because something's not documented or I haven't memorized how it works. So why is that the case, right? Like in both cases, it is Java code, whether it's Java code in Gradle or whether it's Java code in Mockito's application. In both cases, I'm using the same IDE, IntelliJ, which is a very good IDE. The problem here is that in the Gradle code, like in most build tools, we are configuring the build tool using these global mutable variables. Like I'm mutating JVM args. I'm mutating compiler args. Anyone could mutate it, anyone could read it. And I have no idea who's mutating and who's reading it, and neither does the IDE. So just because I wrap the global mutable variable in a getter and setter doesn't make it any less global or any less mutable, as you know. And IDEs are not good at managing global mutable variables. This is in contrast to application code. Like if I look at some random file within the Gradle code base, sorry, Mockito code base, It doesn't use global mutable variables. It uses classes, methods, extends, overrides, all the standard object-oriented stuff. The IDEs are very good at navigating. So that's why IDEs, despite being the same IDE in the same Java language, are very poor at navigating your build scripts, like in Gradle or Maven, even though they're excellent at navigating application code. So I showed you the Gradle Groovy DSL. The Gradle Kotlin DSL has the same problem. It's a bit better because the types in Kotlin do help, but the global variables, as you know, are just a problem in typed languages as they are in untyped languages. And Maven, despite not really being code, has a similar problem. If I didn't know what exec does, there's no way for me to jump to use my IDE to figure out what exec does. I just have to memorize it and know everything in order to use the tool. And that's not the experience you get day to day in Java, where you can navigate in your IDE and figure things out as you go along. Last area I'm going to look at is programmability. So every build tool has a bunch of built-in functions. Every build tool has plugins. Every project that gets into any reasonable size needs things that are not in the built-ins and not in plugins. Netty, we saw earlier, needs to compile C code using GCC or Clang. Mockito needs to mangle class files in order to make the mocking work for some technical reasons. So every build tool in a real project tends to need to have customizations. As an example customization, let's say I want to save the project line count as a line count txt resource file for use at runtime. So this is a bit artificial and contrived, but it's representative of the many weird things you have to do in real projects. Doing this in build tools like Maven or Gradle isn't impossible, but it can be surprisingly difficult and surprisingly tricky. So here's an example implementation using the Maven exec plugin. It shells out to sh-c and runs some shell code. It doesn't run on Windows, of course, because Windows doesn't have sh built in, so that's one problem some of you may encounter. There are also other problems. Can anyone spot the bug in this shell script or Maven config? So this is the most simple possible Maven config for the most popular build tool in Java ecosystem. It's buggy, and we have like 50 people here. Can anyone spot the bug? That's one bug? Yes, the ampersands. Any other bugs? Yes, that's right. So the ampersands and the triangle brackets need to be escaped in order to make this valid shell in XML. So 2 people could spot the problem out of 50, so you're like a maybe 4%, 5% chance of catching these bugs during code review. Otherwise, you just slip into your code and cause problems. So yeah, it's tricky, right? It's not so easy to get this right, even though the requirement is a completely trivial requirement. This should be a student project for 10 minutes to get it right. And here I have a whole room full of people having trouble finding problems. There are other ways to do this, whether a bash script runs outside of Maven, whether you use Ant, whether you use custom plugin with a Mojo API. All of these are very tricky given how simple this requirement up here is. Gradle has different problems. So Gradle, this is a Gradle Kotlin implementation of the same feature, counting the lines and putting them in text file. Gradle runs on JVM, so no Windows problems. There's no bash XML escaping problems. It's just Kotlin or Groovy. But there's a lot of other tricky things, and making sure you have your depends-ons, input files, do first or do last, and stuff all wired up correctly. And this can be very subtle and hard to get right. There's also a bug in this one. Let's see if we can spot it. So in this case, the bug is a non-deterministic performance problem. So you can manually test it. The output will always be correct, but sometimes it'll just be randomly slower for reasons that might be hard to explain. So let's give you guys like 15 seconds, 20 seconds, and you can spot where the bug in this thing is. So you register these process resources, depends on generate line count. Generate line count, we list the Java folders, we walk them, we walk top down, we register some inputs and outputs. We end up writing the output file to this value. So that's how it's meant to work, but why would it misbehave? So the bug here is that we were registering an input, the wrong input folder as the input. So we've said source main is the input, but we only really care about source main Java, which means that anytime you touch source main template, source main config, source main any resources, it'll reevaluate this task even though the output will be exactly the same. So we have to spuriously be reevaluating tasks that don't need to be reevaluated. And this is very tricky, right? You won't catch it during manual testing, the output will be correct. You won't catch it during code review, none of you will catch it. Your colleagues won't catch it. when your plugin authors design their plugins, there'll be similar bugs that they won't catch because they are just people as well. And that's how your build tools tend to become slow and flaky over time for reasons no one can explain. And that's why people tend to have this kind of best practice of don't touch a build tool because you will screw it up. As I showed you, it is super easy to screw up your build tool config, even for such simple customizations. So that's the problems with Java build tools. Like the performance is kind of compared to Java, which performance is great. ID support is there, but also mediocre compared to Java ID support, which is also known to be excellent. And programmability is very tricky and error prone. It feels like writing Bash and CSS rather than writing Java, which is known to be quite easy to learn and quite easy to connect together components with a type checker helping you make sure everything works. So that's why build tools are hard for users, but why doesn't someone just go and make a better build tool if the current build tools are not good? And I think the reasons for that is that build tools are very hard for implementers of the build tool or designers of the build tools as well. So every build tool starts off simple. You start off with something like JBang. Who here has used JBang? Few people. Basically lets you run a Java program single file, but you can rather than just running Java, foo.java, you can also add dependencies and add Java versions and automatically download and cache them. Very convenient. But as the program grows, it tends to get messy to have a very long list of flags, and you end up with some kind of hierarchical config quite often. So for example, you might end up with TOML or YAML or JSON, which is popular in the JavaScript land. Like this is an example GitHub Actions config, which can be thought of as a build tool of sorts. And you'll see there is a hierarchy instead of a flat list. But when you look at it a bit more closely, you'll see that the hierarchy is not actually what you care about. What you care about are these variables that you're defining somewhere, passing into a function call of some kind and using in the function body. You are defining a job here and you're referencing it here. You're defining a shared workflow template here and you're referencing it here and here. So although it looks like a hierarchy of different config values, they're not just arbitrary config values in a hierarchy. What you actually care about when you think about these build tool configs is the graph. In this case, at GitHub Actions, you have the blue inheritance graph, you have the red data flow graph of who's passing a message where, and you have the green dependency graph of the different steps in your build pipeline for GitHub Actions. So that gets to why build tools are complicated. Like everyone wants to just say, I'm going to pass in a few key values, it's super simple. But when it really comes down to it, build tools are graph computation engines. So every build tool, if you look at the example below, needs to handle things like, I have multiple modules. The modules look kind of the same, but they're not quite the same. Like this one has no upstream class path, this one does have an upstream class path. And so we need a graph because the build tool needs to know what order to run things in and what can be parallelized and what can't. If your build tool doesn't have parallelism, you probably won't want to use it. You need computations because class files and jar files and assembly jars don't create themselves. Somebody needs to say how these things are created, whether it's in Bash or Groovy or Kotlin or Java or XML or something else. And it needs to be templated because the different modules in the build are often very similar, although they're not quite the same. Some will have different upstream dependencies, some will have special class path configuration, some have special compiler flags, and someone's going to have a special source folder layout for some reason. So it needs to be templated, but also customized at the same time. And there are many ways to do this. We saw GitHub Actions, the needs keys form the graph, the bash snippets are computation, curly braces form templating. Maven has the dependencies or managed dependencies doing the graph, the plugins doing the computations, and the templating being done by parent POMs, or in Maven 4 you have Maxin POMs. Some tools try to hide this in plugins, but that doesn't actually solve the problem. If your plugin authors have trouble managing this templated graph, that's how you end up with plugins that are buggy, or plugins that don't work well with other plugins because the graphs don't really connect together well. And this makes build tools fundamentally quite a complex problem. So looking at this list of things that build tools need to do, ignoring anything Java specific, like this, ignoring class files, compilers, jar files, dependency management from Maven Central, just the build tool things without Java, actually it's quite a long list of things, and this is not even complete. Like you need to have custom tasks of some kind, need to run things from CLI, redirect to this, order things, pass data. Like you pass data on disk, you pass data as JSON, you pass data as protobuf. All sorts of decisions you need to make. How do you customize an existing task that's already there? For example, we saw Gradle's task.named versus task.register just now. One is a new task, one's customizing an existing task. So if you look at the Gradle config we saw earlier, which we had a lot of API surface area that's quite complicated and had bugs that you couldn't find. It's not that Gradle wanted to make a complicated API, it's that in order to satisfy all these requirements and answer all these questions, Gradle had to have all these things available for the user to customize, and that's why Gradle became complicated. So that's why build tools are hard for implementers as well. Like any build tool you see will have some kind of graph, computation, configuration kind of embedded in whatever syntax it uses. Doesn't matter if it's XML, Python syntax like in Bazel, Groovy or Kotlin, you have to manage this graph somehow, have some computations done somehow and template it somehow. So next, let's talk about one open source project called Mill, which tries to make progress in this area. So Mill is an open source build tool targeting Java, Kotlin, and Scala. It's a smaller project. It's not the industry standard like Maven or Gradle. It's a small number of maintainers, committers, contributors. I do know people using it at Disney or at Netflix, but it's like teams within the company, not the whole company. Mill syntax is using the Scala syntax rather than Kotlin or Groovy like in Gradle, so it might be a bit foreign. But hopefully it's not too foreign, like packages, imports, comments, objects extending classes. The only thing that might be foreign maybe is def, which defines a method in Scala syntax rather than fun like Kotlin uses. But multiple inheritance and multiple interfaces, all that stuff works as you'd expect. Mill from the command line lets you use a /mill script typically. This is similar to /mavenw or /gradlew. So if you say /mill foo.compile, foo.run, see this is a foo module, so it's foo.compile, foo.run, foo.test, foo.assembly, you can use show to show the output path and run the assembly later. All standard build tool things. So I think where Mill is interesting is where it goes beyond the standard build tool things, and that's what I'll talk about next. So the areas of performance, the areas of ID support, and the areas of programmability. First, performance. In order to measure performance of a build tool against another one, you need a big code base that's built using two build tools. And these don't really exist out in the wild because no one wants to maintain two build tools on the same code base. So we had to make our own synthetic example just as a proof of concept. So we took the Netty code base we saw earlier. It's quite a big code base, 50 sub-projects and lots of files, lots of classes, lots of tests. We converted it from Maven to Mill. There's some automation to help, but you still have to tweak some stuff manually. Automation is not 100%. And we got all the tests passing in both. So we are quite sure that it is a realistic build. All the flags work, all the compiler flags, JVM runtime flags, dependencies are wired up, and so on. And once we did that, we could run some benchmarks. So for example, we saw the parallel clean compile all benchmark with Maven took about 50 seconds. With Mill, it takes less than 10. And I can show you this now. So if I go here, do ./mill, clean, and ./mill compile. I've actually gone through the logs and counted all the compiling XXX Java files and added them up. It does add up to the same number. So it's not that we're missing any files. It's just that we are able to compile everything in 7 seconds, where Maven took about 50. And it's not because we did something special with the compiler, it's just that the compiler should be able to compile the whole thing really quickly if it is kept warm in memory, if it's allowed to get JIT optimized, and if you remove a lot of the overhead that typical build tools will give you. Another interesting thing to look at is incremental compiles. So if I make a change to a single file, for example, let's say I go to like here and I just add a comment like hello world. If I use a non-clean compile, so this allows Mill to reuse the previous compile outputs where possible, you see it ends up compiling very quickly because there's nothing much for it to do. We only added a comment to one file and we don't need to recompile the rest of the code base. But if I go and do it using Maven, non-clean, we maybe end up waiting a while for it to really figure out that there's nothing for it to do. So that's the kind of the difference between Mill and Maven in terms of performance. It's not that Mill does anything magic, it just kind of tries to remove the overhead that many of the existing build tools have, whether from cold JVMs, whether from there's general inefficiency wrapping the actual command you want to run. We did a similar comparison with Gradle. So the difference between Mill and Gradle, instead of being 4 to 6x like Maven, is about 3x for clean compiles. So Gradle is significantly faster than Maven. I think the Spring Boot guys have published a blog post about how migrating to Gradle really sped up their workflows. It is faster. Mill is just faster still. Gradle also has an incremental compiler. Mill's incremental compiler is just typically a bit smarter and a bit less overhead than Gradle's. Other interesting areas of performance improvements, Mill works quite well for large code bases. So apart from supporting multiple languages, including things like Android, it works well when you have like hundreds of modules, which other build tools like Maven or Gradle tend to have slowdowns, whether, for example, the Gradle configuration time or the Maven initialization time. Selective test execution comes built in with Mill, so if you have a code base, open pull request to, you can easily make Mill diff the branch from main and look at only run the test for the modules that are downstream of the code you changed. So in theory, any build tool should be able to do this. Every build tool knows what module depends on what other module, right? So they all can just do a breadth first search and run the downstream tests. But they make it quite difficult, so most people don't. Whereas Mill has it built in, it's quite convenient. You don't end up running all these irrelevant tests that could not possibly be affected by the code you changed. Last thing is mentioned here is automatic build profiling. So the most common question people ask about their build tool is, why is it taking so long? And Mill, it gives you the answer kind of out of the box. So if I go back to netty and I do a clean compile, so every Mill command automatically generates a profile dump for you in this Mill Chrome profile.json file. So this is not something you're meant to read yourself, but it's something that is a standard format supported by the Google Chrome team. And anyone who has a Chrome browser, which is probably all of you, can go to chrome://tracing, and you'll see that your browser comes with a built-in parallel profile explorer. This is often used by web developers trying to figure out why their website is being slow. But you can use it for all sorts of things. Let's generate the correct syntax here, format. So here, if I just drag my Chrome profile into Chrome, I immediately get an explorable view of where my time is going. So it took 9 seconds or so to clean compile netty in the last run. Where did the 9 seconds go? Well, you can see the first 1 second we were quite well utilizing all our cores. We then got bottlenecked on common compile. The bottleneck cleared, then we got bottlenecked again on buffer.test and transport. Here we're making decent use of CPU, though it's still a lot of downtime. And then lastly, we got bottlenecked on microbench, holding up the whole build at the end. So hopefully, even if you know nothing about Mill and you know nothing about netty that we are compiling in this last command, you already have a good intuition for where the time is going. And if we wanted to improve this, what could we do? Maybe we want to break up microbench into smaller submodules that can compile in parallel. Maybe common could be broken up as well. Could it be multiple parallel modules that different things can depend on? So that's the performance angle, I think, for Mill. It's just straight line faster than the other build tools, Maven or Gradle, not by magic, but just by optimizing away the overhead. And it has some nice features like supporting large code bases, selective testing, automatic build profiling, so your build tool doesn't feel like a black box like it often does using Maven or Gradle. Next thing to talk about is IDE support. So Mill has, I think, better IDE support than most other build tools. It's not perfect, it's a younger project and still has some edge cases and bugs, but it works very well. And let me show you what this means. So over here on the left, I have the Mill config for the Mockito error-prone submodule. It's one of the submodules within the Mockito codebase. And on the right, I have the Gradle config for the Mockito error-prone submodule. So the first thing you may realize is that they look almost exactly the same. The syntax is a bit different. This is test jvm args plus equals. This is def fork args equals. But apart from the syntactic differences, because one is Groovy, one is Scala, the contents is all the same. Because this module needs these flags to run, it needs these flags to compile, and Mill doesn't do magic. Mill and Gradle, Bazel, any build tool will need to provide these correct flags. But where things are different is that where the Gradle build is configured using these global mutable variables, which are famously hard to analyze both for humans and for IDEs, the Mill build is defined using method definitions. In Mill Scala syntax, def is a method definition, and overrides. You can see IntelliJ knows that this is an override over here. So not only can I ask for things like documentation and type signatures using my standard like pcat definition hotkey, I can also jump to the override very easily. I can see where the override has its the overridden method has its documentation. I can see its type signature, a sequence of strings. I can see its previous value. This is something we did not have in Gradle. I can see its previous value was an empty sequence of strings. In this case, it's trivial, but other cases it may not be. And I can see where it's used, F7. I can I can find usages not just in my own build config, but also upstream in the mill build. So I can see how this thing that I'm setting, fork args, ends up affecting other parts of the build and affecting the thing I care about. For example, maybe I want to see how does fork args affect my running task, because I run it later, it uses a fork args, but maybe I want to see how the logic goes, something's going wrong or something's behaving not quite as I expect. In Gradle, you can't do that. In Gradle, you're basically stuck. You can't get anything in your IDE. But in Mill, it's very easy to say, well, fork args is here. Fork args is a method that gets called by this runner method. I can jump into here if I wanted to, but for now, let's just skim over it. Runner is called by run background task and run fork task. Run fork task is called in run. So this is interesting because it is the same workflow that you guys are using every day, day in and day out in your application code, whether Java, Kotlin, Scala, nowadays even TypeScript or Python. If there's something you don't understand, you just navigate around, find usages, jump to definition, and you never get stuck just because something's not documented and ChatGPT doesn't know about it. I showed you going downstream. I can also go upstream, like find the main class, maybe. No documentation, that's bad. But what is it? Well, you can jump to it. I can see there's no document, but I can see the implementation. It calls this final main class opt thing. Let's say you don't know what this does. Again, no documentation, that's bad. But again, I can jump to it. And I can see that, okay, final main class opt, it first tries to call the main class method. What's this? This is any explicitly specified main class from the user. So by defaults to none, but the user can pass one in. If there's one, it uses the user's specification. If there's none, it calls all local main classes. All local main classes, it seems to use class graph, which is an open source project to scan your class files and look for public static void main methods. Okay, if it finds an empty sequence, that means there are no main classes, it reports an error. If it finds one, it uses that. If it finds multiple, it raises an error saying that, okay, multiple main classes found, here's a list of them, please specify which one you want, I can't choose for you. So the syntax may be a bit foreign because it's a Scala syntax rather than Kotlin, Groovy, or Java syntax. But hopefully the ideas behind this are very familiar to you. The idea of jumping to definition to figure out where this thing in my build is coming from and what it does. Find usages to figure out where it's being used elsewhere and going to those usages to see how it actually affects my build. So if your build works perfectly and you never need to touch it, this is all not interesting to you. But when something goes wrong, whether you misconfigured something, whether some plugins misbehaving, whether two plugins work well on their own but don't work well together, being able to navigate around your build, just like you navigate around any application code, becomes very valuable in figuring out what your build is doing and making it kind of approachable to people rather than a black box. So that's the IDE support demo. So that's why I think that Mill's IDE support's very good. I think it's better than what we have in Maven or Gradle, despite being a younger project. Lastly, I'm going to talk about programmability. So I think the most interesting thing about programmability with Mill is that where most build tools require extensions to be published as plugins or build against a special plugin API or plugin interface, Gradle has its plugin API, Maven has its mojos, and so on. Mill lets you just write code and call libraries from Maven Central to do whatever you want. So you don't need to find a foo plugin to do foo in your build, you just use the real foo. The foo plugin may be half abandoned, half baked. The real foo usually is quite well maintained and usually quite well documented. So Mill just use the real thing rather than trying to find some plugin or half bake your own plugin. So what does this mean? Let me do this one live. So here on the right is an example of the minimal Mill build for a single Java module in the foo subfolder. I say object foo extends Java module, you extend the class to get all of its defaults, default sources, default resource folder, default compile step. You can override things if you want, but if you don't want to override anything, then you just have empty bodies, just get all the defaults. I can go to this in my terminal, foo.compile. Okay, it needs to warm up a bit, and then okay, it's done. So let's say that I don't want the defaults. Let's say I want to count the lines of code in this module and add it as a generated resource file for use at runtime. How do I do that? So in Mill, everything is a task and every task is a method. In Mill's syntax, methods are defined using def, so maybe def line count equals task. And within this method, I can call other methods. For example, I can call foo.sources. If you're not sure which method you want to call, again, you can ask IntelliJ. IntelliJ is very helpful here. VS Code works as well. So in this case, maybe I want all individual source files fed into a Java compiler, so I don't need to walk the file system myself. Map each file to its file path. Let's say os.read.lines, and then get the size of the lines and sum them up. So that's all I need to do to define a custom task in Mill. The only thing that's unusual here maybe is that you use def to define a method, and the return keyword is optional because it just returns the last value in the method's body. So now I can do ./mill show foo.line_count. You can see line count is 17. I can do mill inspect foo.line_count. You can see that we automatically copy your Java doc for you. We copy the fully qualified name of the method for you. We capture the inputs for you, so you don't need to list them out separately like using depends on in Gradle. Just makes it a lot more convenient to write a very simple method and have it become a build task. So we've done our line count task, but we haven't wired it up into our resources. To do that, resources like in Mill, like everything else, are just tasks, and tasks are methods. And the way you customize methods is typically by overriding them. So I can do override def resources. Again, you can ask IntelliJ if you're not sure which one you want. Let's say call the super method, and then I want to write to this task.destination folder, which I'll explain in a moment, my line count as a string. And then I'm going to append this, a reference to this, to my resource path. So what's this task.destination folder that I'm writing to? So the biggest problem in most build tools is that the file system is the world's biggest global mutable variable. Anyone can read from anywhere, and you can write from anywhere. You don't know who can safely be run in parallel and who, if run in parallel, will stomp over each other's files, creating race conditions. You don't know what you can safely delete and what you cannot safely delete, because if you deleted something else, depending on that file, will blow up. It just becomes a very big mess on the file system, trying to manage it and keep it sane. And that's why build tools often ask you to clean compile things, because someone screwed up the caches on the file system in that way. So in Mill, we still need to use file system because class files, jar files need to live on the file system. But what we can do is we can say that every task has its own local folder for it to write to, that it can write to, but other tasks can only read from. So I do mill show foo.resources now. You'll see that I not only have my foo/resources folder, which is my super resources here. As you know, we overrode it, so it's now called super. We also have out/foo/resources.dest, which is this task.destination folder we appended to the resource path. So by putting everything in a task local readable writable file system, but globally read-only file system, Mill turns the file system problem from a global mutable variable into locally encapsulated mutability, but globally read-only. And it really helps keep things like straight, both for humans as well as for the tool itself. And now if I do mill foo.run, you can see that we are able to use the line count that we created at build time, get stored on disk in out/foo/line_count.json. You can see the value here together with some metadata to aid in invalidation. And we can use it at runtime in our application. So this is a bit of a silly example. No one actually wants to count lines and put them in production. But it just shows how easy it is to write custom code to do the thing you want, using all your normal object-oriented concepts like method definitions, method calls, override, and super. All things you already know, rather than having to learn a whole new like API of task.register versus task.named and all that kind of thing. So let's take this one step further. Let's say instead of using the line count as a text file, I want the line count as a HTML file. So this is just a contrived example, but let's say I want to use a third-party library like org.timeleaf in my build system. So this is common in other cases. Maybe you want to use a linter that comes from Maven Central, or some packaging binary or compiler that comes from somewhere. How do I do that? So Mill doesn't have Timeleaf, a HTML templating library bundled with it, because Mill is not a web framework, it's a build system. But what Mill does let you do is makes it very easy for you to kind of ask for these dependencies via these magic comment headers similar to the JBang syntax we saw earlier. So I can say Maven deps on org.timeleaf, /timeleaf, :3.1.release. And I can reload my IDE. I think I might need to close it and reopen it. Let's close and reopen it. Let's reopen this IntelliJ. Okay, you can see it's importing the build again. And now I have Timeleaf available in my build system for me to use. So IntelliJ can show you that Timeleaf is available in the external libraries. I can import Timeleaf, for example, context.context. I can import Timeleaf template engine. If I define a new task, for example, the HTML snippet, I can do things like var context equals new context.set variable line count, and then line count. I can do new template engine dot render dot process. I'm going to grab the template from the slide because it's a bit finicky to type out. Template engine dot process this template and the context. Now, if I do show foo.html snippet, you'll see that I now have a task that renders line count using a third-party library at build time. I can see the output on disk in /foo/html snippet.json. See it gets cached on disk like any other build time step. And if I wire it up into my resources, I can do foo.run. And I am now customize my build using a third-party library and some custom code, generate a custom resource file at build time using that I can now use at runtime in my application. And I think what's most interesting here is that in most other build tools, you spend time trying to look for a build tool plus Timeleaf plugin or build tool plus template engine plugin to pre-render your template. So I may have to go learn a lot about a particular build tool plugin API, whether it's a Mojo API or whether it's a Gradle plugin API in order to build your own plugin. Whereas in Mill, although you can have plugins, I can publish this customization in Maven Central for others to use if I want to. It's also very easy for you to just customize things yourself without having to find a plugin. I can use a real Timeleaf, which is well documented and well tested and has a good, well-designed API. I can just use it together with normal code in my method bodies that become the tasks in my build step. So I don't need to go find some plugin that's last updated 5 years ago on GitHub and hope it does exactly what I want. So that's the programmability angle, which I think Mill is pretty cool. The last section of this talk is the idea of object-oriented builds. The obvious question is if other build tools have struggled with programmability, performance, and IDE support for the last 20 years, why haven't they made any improvements there? Like using Maven today versus using Maven 2015, it doesn't feel that different in the IDE, for example. I think what's missing is the idea of object-oriented builds that kind of underlies everything I showed you in these demos. And that's what allows Mill to be a bit simpler than other build tools and work better with your IDEs and the rest of the ecosystem. So earlier we talked about this idea of templated graph computations, and they're complicated. If I design a templated graph computation class, or you design a templated graph computation class, it's going to be a very complicated class, and it's hard to make it simple. But it turns out that everyone here already has a way they've been writing templated graph computations for many years or decades by this point. And you write templated graph computations every day. It's just called object-oriented programming. So what does this mean? Like you write OOP, you write Java. So when I say object foo extends Java module, like you already know what this means. The object gets all the methods from the class. The methods maybe call each other and return data to each other. You return their return value to each other. So like foo.sources returns a value to foo.compile, returns a value to foo.classPath, together with resources gets used by foo.assembly. So you know how this works just because this is a class and I'm extending it. So when I add a new method, def line count calls all source files and then does some processing on it. Or I override an existing method. I call the new method I just added, and I call super. I don't need to teach you anything for you to know exactly how this will affect the graph we have in the top right. You know that assembly will call the override of super, of resources, rather than calling the original one. You know that super works by keeping the original method in place, so the new override can call it. You know how this calls line count, this calls sources. So you know how all this stuff works because this is just vanilla object-oriented programming. And if I want to template this, I can just turn foo from a singleton object into a class. Mill calls it a trait for technical reasons, but it's basically a class, and I can extend the class from multiple objects, and I've now templated my graph. So everything you know about object-oriented programming works here. You can have subclasses that have more customizations that get used in multiple places. If I want to customize foo or customize bar, I can just open up curly braces and put more customizations and overrides in those particular modules. All these object-oriented concepts, all just apply here. It means you can very familiar way for you to manipulate this templated computation graph of the build tool without having to first learn a huge laundry list of new build tool graph concepts that you do in most other tools. So once we have this graph, Mill can then do the build tool things on your behalf. Things like compile and line count are obviously not dependent on each other, so they can run in parallel. Assembly depends on both, so assembly needs to run after. Mill can see that every method has a fully qualified name. That's how object-oriented programming works. You have foo.linecount, foo.compile, foo.assembly. So we can not only use that from the command line, we don't need to have a special command line syntax, a command line name that's put in a string somewhere. We can also use that as a place to put the things on disk. So like foo.linecount gets out /foo/linecount.json, put its metadata. Foo.compile gets out foo.compile.json, put its metadata, and out foo.compile.des to put its file outputs. And these will never collide with each other because methods in JVM are unique. So you have foo.compile, foo.assembly, they each have their own place to put its stuff. No worries about collisions, race conditions, stomping over each other, and so on. Lastly, Mill can do automatic invalidation for you. So Mill can say, resources, you touch the resource folder. This is called super resources because we overrode it. Mill just does a breadth first search, sees that assembly needs to recompute. Compile and line count do not need to recompute. They're not part of the breadth first search. Mill knows where to find the previous output for compile and line count because they're at this standard location on disk. So we can load them into memory and reuse them as necessary. And Mill knows where to find the previous output for assembly, again because it's a standard location, so that Mill can go and delete the previous output and let you recompute it clean. And what's most interesting here, I think, to me, is that on the left, all you have is very vanilla object-oriented code. So syntax might be a bit foreign because it's Scala syntax, so you use def rather than fun like Kotlin. But basically, you have object extends class, method calls method, override, def calls other method, and calls super. These are all things you already know what to do and how they work. But you don't see any depends on clauses, input file, output file registration, like we saw in the Gradle build earlier. We don't see phase registration, like what phase do things run in, like you see in Maven. You don't see any parallelism-related code, like locks or mutexes or semaphores or executors. You don't see any cache-related code, like cache key computations or cache invalidation logic. So 99% of the time, Mill will handle this for you, and you just write your most boring object-oriented code and close your eyes, pretend it's an OOP program, and it generally just works. So earlier we saw all this long laundry list of things that makes build tools complex and how this affects the Gradle build API, plugin API. And Mill also needs to handle all these things, but Mill handles it kind of by squeezing it into this more familiar object-oriented structure. So we don't have def register, we don't have like a task.register, we have we define a method. And instead of having the name of the task be in this string that ID doesn't know about, the name of the task is a method name the IDs are good at working with. We don't have do first or do last. Instead, the fact that you're calling a method, other method, means that you need to run after the other method returns its value to you. So we don't need to manually kind of jigger the order of the graph in order to make things work. The fact that you call methods in the OOP program already gives us that order. So just to sum up the idea of object-oriented builds, the key insight here is that the whole build is very well modeled as methods, objects, classes, extends, overrides, super. And these are all ideas that you already know how they work. These are all things that IDEs already know how they work. They work 99% the same as they do in any other object-oriented code, whether Java, Kotlin, Scala, Python, JavaScript. It all works the same, it's OOP. And Mill can handle all the other stuff for you, again, like 99% of the time. So 1% of the time you may need to open the escape hatch and tweak something under the hood for performance or something like that. But most of the time, you just hands off, let Mill handle it. You get good performance because you don't have people forgetting to parallelize their plugins, which happens in Maven or Gradle. You don't need to clean because you don't have people or plugins screwing up the cache invalidation, which again, very common in Maven or Gradle. And it makes life easier for everyone. So like me working on Mill, I can do fun things like selective testing our Chrome profiles rather than struggling with these build graphs all the time. We can integrate tools very easily, so we've done that. And for people working on application code, you can spend less time futzing with your build and more time just working on application because the build is straightforward and you already know how it works and how to manipulate it. So on the topic of integrating tools, because it's so easy to integrate external tools, like we saw earlier with the time leaf example, we've taken liberty in the mill project to integrate a lot of the existing tools out there on just upfront. So we've integrated all the linters, all the formatters, all the code coverage tools, all the test frameworks and web frameworks and so on. So hopefully if you want to use Mill to do something, most of the things will already be integrated. You don't need to go and hunt down the plugin. And if you do need something that's not on this list, then hopefully it's not too difficult for you to integrate it yourself, like what we saw earlier with the Mill time leaf example. You can just import the jar from Maven Central and call it programmatically as part of your Mill methods. So this is the last slide. So that's OOP, and this is the last slide. So this basically summarizes everything I talked about. I won't read it out to you. I think maybe the high-level summary is, if any of you have had problems with build tools in the past, have problems with build tools in the present, and wondered if there is a better way, I encourage you to give Mill a try. It's a much younger project than Maven or Gradle. It doesn't have 20 years of battle testing. It is not the industry standard. But it does have a lot of very interesting ideas, and these interesting ideas are not just theoretically interesting, but they correspond into real concrete improvements that affect your user experience. Things like IDE navigation that actually works and lets you explore your build graph. Things like 5 times better performance, or things like easier programmability, where you can just write code with full IDE support rather than struggling with some weird plugin API that is not well documented. These are areas that traditional build tools have really struggled with improving in the last 10, 20 years. I don't think Maven or Gradle have made huge progress there. I think Mill, despite being a younger project, has made quite a decent step forward in making these things better. So the website's mill-build.org. You can see there's examples for getting started in Java, Scala, Kotlin. If you want Kotlin web development, we have a whole bunch of Kotlin web development examples, like Kotlin JS maybe, or Kotlin MVC. And all these examples are downloadable, so you can download the zip file, unpack it, and run it. They are part of our integration test, so they should work out of the box. And there's also some migration instructions and automated migration tools. So if you want to import a Maven build, you still have to tweak it a bit, but you'll get the boilerplate of getting all the dependencies and stuff set up for you. So you won't need to put in too much work. So that's the end of the presentation. I hope you enjoyed it, and I guess you can take questions.